So we can still use the third hand rule for this one, so you don't have to do another hand rule. But for this one, a conducting wire has a current running through it. It will experience a magnetic force when placed perpendicular, that's where this is key, perpendicular inside a magnetic field. Just as a charged particle will experience a force, so our third hand rule, we said, say a particle is just experiencing this magnetic field, which way will it experience the force? So now we're saying, well, if we have a bunch of charged particles in a wire, that whole wire will experience a force. So you can still use your third left-hand rule. So say we have a conducting wire, and it's going into the page. So, and it's placed in a magnetic field as such. It's placed in a magnetic field like this. So our magnetic field is running north to south, okay? And our current, this is our current going in. So the conducting wire is your thumb. It's going into the page, okay? And we'll assume that this is negative, so we can use our left-hand rule. So it's going into the page, and our magnetic field is going north to south this way, then the force is up, okay? So, or north, I should say. So on here, so if a wire was placed like that, it would then move up if once it's experiencing that magnetic field. So now we can calculate this, and this is a formula, and it's on your data sheet. So where we have Fm, okay, our magnetic force, is equal to I, which is current. We've seen that one before. L perpendicular is the length of the wire in perpendicular to magnetic field, and B is magnetic field. You could say B perpendicular and L. It doesn't matter. It just means like L and B need to be perpendicular to each other. Okay? So whichever way it explains it is fine. Now, this was an important application. This was that little motor that you guys tried to make with the wire, and then you put it up on the paper clips, and then you put a magnet underneath. So theoretically, you were inducing, you were putting a current through the wire, and then it was experiencing a magnetic field, and so the wire would have certain forces. So on this part of the wire, it would be forced up, and this part of the wire is going to be forced down. So it just keeps going. Once this wire comes down and around and gets here, the electric current, it's actually a conventional current at this point, will be forced up. So this is actually running with a conventional current. So use your right hand. Okay, conventional means right hand. So every time you see a question that says conventional. So use our right hand. So let's say at this point, our current is going this way. Okay, and our north to south, so our fingers go north to south, and so then our force is up. Okay, so that's why F is up, going that way. And let's try it here now too. So right at this point, our current is going down this way. Our magnetic field is the same, and so it forces it down. Okay, so it's kind of cool because that's how these motors work, right? Is that they, at different points, this will experience force up, this will experience force down. It just keeps turning. Okay? So, and this picture uses conventional current, so use right hand. All right, so another example. If the conducting wire is deflected towards the back of the U-shaped magnet, determine the polarity of the magnet. So it's being forced like back this way, okay? So this one is, just let's visualize it a little bit. So if we were looking at it, like here's our magnet and here's the wire's like going into the page, okay? The way it's kind of pictured here. So if we had, yeah, okay. So it's like here's the magnet, it's going into the page. So here, I would actually draw an X with my wire, so it's going into page. Okay. Oh, and I can use my thumb because I'm using a electric current. So here, it's coming out the negative. Here's my electrons, and that's why I know it's going this way. So I know it's going into the page in my diagram. And then it tells us that it's being forced to go this direction. Okay? So it's getting forced to go to the back of the magnet. So use your left hand. So if our electrons are going into the page and it's being forced this way, okay, then my magnetic field runs up and down like this. Okay? So it's being forced this way. Oh, whoops, I changed my hand. Sorry. So it's running into the page, forced this way, magnetic field points up. So this is south and this is north.
Why did the electrons go down?
Because they're going into the page. So I'll maybe just give you a little visual here. So the way it's set up, if it's like this, and I have my wire, like that, if I'm looking right in, like this, the wire, the electrons are going this way, right? So it's into the page. Yes? Okay?
Yeah.
Okay. So that's why it's like, they're going this way. Forced that way, the wire is.
Probably never get that from that drawing.
Well, you need to look at here that the electrons are flowing this way. And since it's talking about like here's up and down, like this is, you should think about this as north, east, south, west, like the magnet and which way the wire's going, and then the electric current is going into the page. Yeah, okay. So it might take you a bit of practice, but that's how to interpret this question. All right, so let's do a calculation one. These calculations aren't too complex.